Ooh, we focusing? Focus on my hands. Yeah, cool. Okay, so we're on to part 3 now. Part 3 is where we get into the nitty gritty. We'll actually look at some real systems. We look at 3 systems. We look at masses, pendulums, and an LCR circuit, God forbid. And what we need to do is we need to prove these all satisfy the simple harmonic kind of motion equation, if you like, which is, as we discussed in the first part, but just to refresh our memory, this vibe here. Okay, so we just got to prove these. This is true for all 3 systems. Let's start off with the first one. One, hopefully, we should be comfortable with now. If you're struggling with this first one, I have made a video before where the camera angle makes my arse look massive, so that might be worth a look. Anyway, Nicki Minaj, eat your heart out. Right, so we have a frictionless table, and we have a mass like this. Okay, and we displace this mass a certain level from its equilibrium position. So let's say this is its equilibrium position. This is where it's happy or energetically stable or what have you, and we've moved it a certain amount x away. Okay, this is rigid. This isn't going to move at all. And we have pulled it this way, and we're just going to see what's going to happen. What's the equation of motion for this mass here? Well, let's take the box out of its setting and just look at the forces on it. Let's get a good old force diagram going. So, really, with this box, there's only one force acting on it because we've got a frictionless table. There's no need for friction. Gravity, we don't regard in this. Shouldn't be affecting it because, of course, we've got a normal force and all that. So very simply, we've just got a force wanting to get it back to its equilibrium position. And we all know Hooke's law. Hooke's law, nice and pleasing, is that F equals kx, where k is the spring constant, so let's chuck that in now. I will say here, with these, with this particular example, there's always a confusion of a minus sign, because a lot of people see Hooke's law written as F equals minus kx. Just want to say, don't worry, I haven't negated that. I've just put the arrow going the other way, so I have taken the negative into account by putting an arrow with a direction to it. I always think this is more intuitive than having a force going one way, which is negative, because I don't think it's easier to visualise. But if you like to think of Hooke's law as the negative of kx going in the forward direction, by all means, that's fine. Okay, smashing stuff. So we've got a force, which is which is kx, and now we do our classic equation, F equals ma, so let's pop that in there. F equals ma kx. All rather nice. A, we know, is the acceleration of x. Now, this is where that minus sign we were talking about comes in handy. So we go m double dot x, and we get minus kx. So this is where I'm going to put it in here, because we're talking about acceleration of x going in this direction, and we're talking about the force going back in this one. I hope that's all clear. If not, have a think about it, have a play with it, and hopefully it should become clear relatively soon. What we're going to do now is going to take this x over to that side. Here you go, m double dot plus kx, that equals 0. This is already looking freakishly like this top equation. So let's divide by m to get x double dot plus k over mx equals 0. Lovely. We say k over m equals omega squared, so omega equals the square root of k over m. And there, we satisfy our equation because we get d squared x over dt squared plus omega squared x equals 0. Which is what we wanted all along. Okay, lovely stuff. Right, let's move on to our pendulum.